So as you can see, these two lines are...
Hello, I'm Andy Bain, and I will be teaching about logic and proofs.
Now, a proof is when you prove something with a combination of facts and conditions. And there are several parts to a proof. The first one is the given. Now, a given is a known fact. It is something that is true in the case of the proof. An example of a given: you are learning math right now. Yes, shocking, I know this doesn't seem like math, but it is. Another example of a given is angle G is a right angle. Now, as you can see, this is true with this triangle here, but it might not be true for all triangles in the world. The yellow triangle has angle G being an acute angle. However, if our proof dealt only with the blue triangle, then saying angle G is a right angle would be an acceptable given. Now, the next component of proofs is the conditional. Now, the conditional is a framework. It's the basic statement that you'll be using. And it's basically a statement and a result where the result will be true if the statement is true. And these take the form of P and Q. P is the statement, Q is the result. I don't know why they chose to use those letters, but they did, and that's what we use. A conditional takes the form if P, then Q. An example: our statement is x is greater than 2. Our result, x squared, is greater than 4. Our conditional: if x is greater than 2, then x squared is greater than 4. If we are given that x equals 7, then, because 7 is greater than 2, we know that 7 squared is greater than 4. Now, if a conditional is proven false, like if we're given that x equals negative 3, then the statement negative 3 is greater than 2 would be false. That doesn't necessarily mean that the result will be false, because we know that negative 3 squared is greater than 4, because that would be 9, which is greater than 4. So, conditionals, when they're true, when the statement is true, you know the result is true. When the statement is false, it might be true or false. You can't know. So, when they're false, it doesn't really tell you anything. Contrapositives, however, are the ones that deal with it being false. They are where if the statement is not true, the result will not be true, or framed that way specifically. They take the form if not P, then not Q. An example: our statement, the weight weighs less than 100 tons. Our result, I can lift it. Now, in the form of a regular conditional, if the weight weighs less than 100 tons, then I can lift it. If we're told that the weight weighs more than 100 tons, then I might or might not be able to lift it. You don't know. I could be Superman. If we were given a contrapositive statement, though, which is if the weight doesn't weigh less than 100 tons, then I cannot lift it, then the weight weighing more than 100 tons would make the statement part not being true, true, which would make the result not being true, also true. If the weight weighs more than 100 tons, then it doesn't weigh less than 100 tons, so I can't lift it. Next we have the converse. The converse is where you swap the places of the statement and the result. It takes the form if Q, then P. And this is a weird one, because in our example, I like apples is our statement, and I like at least one kind of fruit is our result. Now, our conditional, if I like apples, then I like at least one kind of fruit, would work. But the converse, if I like at least one kind of fruit, then I like apples, seems like it would be a logical fallacy. I mean, I could like grapes or pears and not like apples, but still be liking at least one kind of fruit. Schools want you to learn this anyway, though, even though they don't quite make much sense. Although they are very helpful in the case of if and only if. Now, this is where the statement being true is the only way the result will ever be true. This takes the form if and only if P, then Q. And now our example, our statement is a equals 7, and our result is a plus 3 equals 10. Now our phrasing of this is if and only if a equals 7, then a plus 3 equals 10. And so if you look at this as conditional, if a equals 7, then a plus 3 equals 10. You know, that's true. If you look at it as a converse, if a plus 3 equals 10, then a equals 7. That will always be true. So you know this is an if and only if, because the only way that a plus 3 will equal 10 is if a is 7. And the only answer for a, if you're given that a plus 3 equals 10, is that a will be 7. And statements. This is where both, or even if there's more than 2, if there's 3 or 4, multiple statements must be true for the result to be true. This takes the form if P and Q, then R. An example, our statements could be line AB is congruent to line BC. Line BC is congruent to line CA. Our result, triangle ABC is equilateral. Now our phrase would be in the form, if line AB is congruent to line BC, and line BC is congruent to line CA, then triangle ABC is equilateral. As you can see, both of the statements have to be true for us to be sure the result will be true. Or statements are very similar, except at least one statement must be true for the result to be true. It takes the form, if P or Q, then R. And now you can have P be true, or Q be true, or both be true. An example, our statements are y equals 0 and x equals 3. Our result, xy minus 3y equals 0. Our phrase, if y equals 0 or x equals 3, then xy minus 3y equals 0. So if y equals 0 and x equals 7, then one of those is true, and we can see that it would still be 0. If y equals 12 and x equals 3, one of those is true, we can see that the result would still be true. Now if they are both true, y equals 0 and x equals 3, the result would still be 0. XOR statements, however, are very similar, but they have one key difference. One, but only one, statement must be true for the result to be true. This takes the form, if P XOR Q, then R. Here's an example. Our statements are x equals 0 and y equals 0, and our result, the absolute value of x plus y is greater than 0. Now our phrase, if x equals 0 XOR y equals 0, then the absolute value of x plus y is greater than 0. You can see if x was 0 and y was 2, it would be true. If x was 7 and y was 0, then it would be true. But if both were true, x is 0 and y is 0, then the result would not be true. So XOR is when one of them must be true, but only one. Lastly, we have the counterexample. This is when you provide an example that proves that a conditional, or another phrase, is flawed. An example of this, if a quadrilateral has equilateral sides, then it is a square. And if you were, let's say you're given a problem where someone used this proof and you're told to find out what they did wrong, you would give them the counterexample to show, well, what they did wrong is they didn't consider a rhombus also has equilateral sides, but it's not a square. So you're proving that the result isn't the only result for that statement. That's how counterexamples work.
So, I hope you enjoyed that, learned a lot, and I wish you luck in your next mathematical endeavors. Andy Bain, out.